Hey folks, welcome back to the tail end of, or the back half of Chapter 1. In today's lesson, or this lesson, we are going to look at something called functional analysis, which is a fancy physics term that's more efficient than saying this. It's the act of taking data, plotting it on a graph, making a line, and then using that line to come up with an equation that describes the data. So really in physics, what we do is we love to take measurements to explain what's going on in the world around us. We're a curious bunch, and we like to see if we can use math and numbers and equations to describe events on this planet and in this universe. And in order to do that, we're going to have to develop two specific skills. The first one is to find equations to describe data that's linear. And remember, linear just means straight. In a math sense, that'll be this video. And then the next video is going to be one looking at graphs that are curved. So nonlinear data, we're going to talk about how to straighten those things out so that we can come up with nice equations. I should mention, take a step back here, this handout, which is 4 pages long, it's got an anteater on it. So look for what I call the anteater handout. It is in the All Resources folder. So you'll find that on the website. Make sure you have that printed out so that you can fill things in as we go. This is something you're definitely going to want to actually try, the graphing by hand. And make sure you've got yourself a ruler or straight line drawing device to make your life easier. So this lesson, we're looking at linear functions. These are graphs that are already straight. We're going to talk about all the good stuff that goes into a graph. And it's a bit busy. This will be a long video, but you'll be really, really good at this by the end, especially with a bit of practice. So, said we're a curious bunch, us physicists, that includes you now. We have designed an experiment to determine how fast an anteater walks. It's going to go for a little cruise and tow some paper through a ticker tape timer. And maybe we end up with this kind of information, some time and distance data. Now what we have to figure out with this data is which quantity goes on which axis of the graph. So time is the independent variable as opposed to the dependent variable. I'll just put it all on the screen. So the time is the values that we chose, or the values you choose when you're the experimenter. So this experimenter, they decided to measure at 1, 1.5, 2.5, and 3 seconds. They did not have any control over how fast the anteater was walking. So those values, the distance the anteater walked, that depends on the nature of the anteater, right? What kind of mood it's in that day. And the independent variable, the one that you choose the values for, always goes on the horizontal x-axis. And the dependent variable that we don't have control over, that depends on nature, it goes on the up and down, the y-axis. So let's go fill these values in, just to give you some numbers that'll work nicely for this. So now that we've got the data, we have to talk about all the good stuff that goes into making our graph. So I'm going to switch windows here if I could. This is actually the bottom of the 4th page. I want to go over a few of the important things that we put into every graph. And we're going to start actually not with the title, but with the axes. What we do in physics as physicists is we always darken our axes. I'll show you what that looks like in just a moment. That really just means we're going to grab our ruler and draw lines along the x and the y axis. We are going to label our axes so people know what they are. And then with those axes labeled, we have to remember to include units. And for now, let's sort of scroll back to the graph and just get that done. So here's what I mean by darkening. So here's my graph. I'm going to grab my ruler, and I'm actually doing this with you, right? I've got a ruler sitting on my computer screen here. We're going to darken these axes. So you don't have to scratch through the page and make it super dark, but I want to be able to see, there you go, that we can draw a nice dark line along the x-axis and then also along the y-axis as well. And really, that's going to set up the edges of the graph nicely for us and sort of show us where just where the edges are. It ends up looking really, really nice. we go. So we're going to darken those axes. We're going to label the axes. It's the next thing for us to do. So we said time is going to go down on the x-axis. Leave yourself some room to put the scale in there. So maybe I'll drop down here and I'll put time. And we want to put units in. The units are seconds. And then we need to label the y-axis. I'm going to spin myself here. Let's call it distance. Again, leave yourself some room to put numbers in there. And the distance was measured in meters. So we've darkened the axes, we've labeled the axes, we've included units on those axes, so that's great. The last thing we want to do actually before we do that, let's go up to the title. For the title, we don't really give people creative control. We do this. Y versus X. So what that means is we take whatever we've put on the y-axis, and then just say versus, and then we just put in whatever the quantity is on the x-axis. And then once we've done that, we underline it. So let's scroll back up to the graph and do that. So my up axis, the y-axis, is distance. You can write the whole word, or you could just put like D for distance. It doesn't matter. Maybe I'll shorten it. I'll call it dist. The distance, and then we put versus, and then our x-axis was time. So distance versus time, and then we give it a nice ruler straight underline. There it is. Well, it's looking good. Getting excited. I'm such a science nerd. That's okay. Don't hold it against me. Now, the last thing we have to do is scale both of the axes. And I think probably in math class you've just done like a guess and check method to figure out what the scale is. But it turns out that in physics we don't do that. There's only some specific numbers we're allowed to use. And those numbers are 1, 2s, and 5s. And then you can play around with where the decimal goes. So if you want to graph something smaller, it could be a 0.1 or a 0.2 or a 0.5. Or a 0.01, a 0.02, a 0.05. Or if the numbers get bigger, maybe I'll put an arrow showing you could go that way and get smaller. If the numbers need to get bigger, it could be like a 10, a 20, a 50. Or a 100, a 200, a 500. So it goes off on that end too. But we just stick to 1s, 2s, and 5s. You can't Frankenstein them together and say, oh, I'm going to go with 15 because it's a 1 and a 5. No. It needs to be like a 1, a 2, or a 5. So you couldn't scale at 15. You'd have to decide if you wanted to go with 10 or 20. But you can't go in between. Even numbers you might think like, oh, 25, that might work well. It doesn't. You have to just trust me. Stick with 1s, 2s, and 5s. So I want to show you a little trick on how we can use our calculator to help us figure out whether we should go to a 1, 2, or 5. So let's scribble this in the bottom. To find your scale, here's what you want to do. Take the biggest data value you have to plot, the biggest data number, and then divide by the number of boxes on that axis. And then what we're going to do with that is, the calculator is going to spit out an answer. We're going to round up. So let's look at what that means by using some of the data. So if I scroll up to, there's our data table. Let's do the time axis first. The biggest value we have to plot is actually not 3. We have to include that uncertainty. It's 3 plus the 0.1, so it's actually 3.1. So on our calculator, we're going to type in the biggest number we have to fit on that axis, which is 3.1, and we're going to divide by the number of boxes. We're talking about these as the boxes, just in case it's hard for you to see. So the sort of bigger boxes is what we're looking for. Those there. So there's 1, 2, 3, 4, 5, 6, 7, 8 big boxes. So 3.1 divided by 8. The calculator spits out 0.3875. That number will not be very fun if you try to scale every box worth that. So now what we're going to do is we're going to round up to the nearest appropriate number. So 0.3875, you can't round down because you'll run out of space and you won't be able to put the thing on the graph. We want to round up, we're going to go all the way to 0.5. So that means every big box on the time axis is going to be worth half a second, 0.5. And you can actually skip some of the boxes if you don't want to label them, if it gets a little bit tight to put the numbers on an axis. So you could label every second box as like a 1.0, 2.0, skip a box, 3.0. It's up to you, sort of how much you can fit in there. So there's the time axis. Now here's another really nice thing to figure out. What are the tiny boxes worth? This is going to be very, very useful to us. So we want to know, what are those little guys worth? There are 5 small boxes that make up 0.5. So 0.5 divided by 5 means every little tiny box, I'm going to make a note for myself, is worth 0.1. So a tenth of a second for every tiny box. Let's do the same trick for the distance. Grab our calculator. Remember that the biggest number that we have to plot on the distance axis is not 1.32. You have to add the uncertainty because we are going to show that on the graph. So that's actually 1.4 divided by, I think there's 10 boxes. Let's double check that I'm right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so good. 10 boxes. The calculator spits out 0.14. We have to round up to the nearest appropriate scale, which is going to be 0.2. So every big box is going to be worth 0.2 meters on the distance axis. So we'll squeeze all those values in there. And I know our data points might not go like all the way to the edges of the graph, but when we draw our lines, we're going to make the lines go all the way to the edges of the graph, so it doesn't really matter. The line is the most important thing. So we got that all scaled out, which looks good. This thing is finally ready to, oh, no it's not. Let's do the one little trick again, my apologies. Let's figure out what the tiny boxes are worth on that y-axis, the distance axis. So there are 5 boxes that make up 0.2. So I'll show you on the calculator what you can do. You say, okay, 0.2 is made up of 5 little boxes. So every tiny little box is worth 0.04. Which is actually a semi-tricky number to work with, but we'll make it work. So what I want you to do now, I'm going to pause the video and do this in just a moment, is I want you to go and plot the data points on the graph, but don't worry about the uncertainty. So just get those 4 data points on. I'm going to pause the video. When I come back and restart it, it's going to be full of data points, 4 data points on there to go. So there's my graph with the 4 data points. Again, let me know if you have some trouble putting data points on there, but I think you should be okay. It just takes a little bit of time sometimes. Now, the next thing we want to add to those data points before we draw any lines is that uncertainty. So we draw these things called uncertainty bars. And I'll show you what it looks like. They're pretty darn easy to put in there. For all of the time values that we recorded, we were uncertain about a tenth of a second. And looking at our scale, we've put this little reminder, which is cool, that a tenth of a second is 1 little box in either direction. So that means although we think the data point should be right there, it could actually go 1 little box to the left. So we put like a little goalpost, and then 1 little box to the right. We put a little goalpost. And every data point has that uncertainty on the time. So we want to show that these data points actually could be anywhere between these little goalposts we're putting in. Right there, so 0.1 to the left, 0.1 to the right on all 4. And then we want to join those things onto the data points. So we're going to make what look like maybe little TIE fighters or something. There we go. And we want to do the same thing on the up and down, the distance axis. We've got this uncertainty of 0.08, which is going to be 2 little boxes up and 2 little boxes down. So we're going to go 2 little boxes up, put a horizontal little line and then 2 little boxes down. Oops, 2 boxes, there it is. And we're going to do that for all of them. And when we go to join these ones onto the actual data point, because we've got sort of a further way to go or a longer way to go, you probably want to grab your ruler and make it nice and straight. Always we want to make nice straight lines if we can in physics. You'll have to pardon my ruler when I do little line segments. It's hard on the computer screen. But the longer ones look better. There we go. There we go. So what that's showing us, don't add this into your notes, but we think the data point is smack dab in the middle, but you'll notice we've kind of made like a little rectangle. And what we're admitting to people, and we have to do this, is that because of uncertainty, that data point could be anywhere inside of that rectangle. We think it's in the middle, but it might not truly be. So now we're going to draw 2 lines. The first line is called a line of best fit. And what we do for a line of best fit is we want to skewer the data points, I guess, the best that we can. And data points in real life are not going to be perfect. There might be some wiggle. And that's okay. That's just how it goes. What I would like us to do, just so that we all have the same best line, is actually just join. You'll see there's 2 little circles on the page. I'd like you to just play connect the dots between those 2 circles. And that's going to be our line of best fit. And you should find that it pretty much skewers those 4 data points, or is awfully close anyway. There we go. You can see I've just about hit the data points. This data is actually freakishly straight. It probably is not going to be that straight in real life. And you'll notice what I've done with the line is I've actually gone like edge to edge on the graph. Even though our data points didn't take up the whole graph, we used the whole graph. And I'm going to label that as B for best, because there's actually going to be a second line on there in just a moment. Now the second line we draw is called the maximum line. It's the steepest line we can make with the data points. And in order to draw a steepest or maximum line, what we like to do is we like to hit the bottom of the first error bar, and then we go all the way through the top of the last error bar. So, or uncertainty bar, I guess I should call them. So I want you to try that out. Grab yourself your ruler, draw a line that goes from the bottom of the first error bar, or uncertainty bar, through the top of the last uncertainty bar, and then drag it all the way to the edges of the graph. Don't stop at those 2 spots we're going through. Make it fill up the whole page. I think I put those little squares on there so that you could potentially go through the squares, but I think it actually misses one of the squares. So I want you to actually go through the uncertainty bars instead. This will be a better line. So maybe something like that. And we want to label that as M for max. That's the steepest line we can make using those data points with the uncertainty. So now what we're going to do is we're going to have to find the slope of those lines. So we're going to draw something called slope triangles. So let's go back to the best line. Let's start there. What we want to do when we draw slope triangles, and that's going to help us find rise over run, by the way, is we want to look for what I call nice spots. And nice spots are where your line crosses right on top of some grid lines. Now keep in mind, even though you and I just played connect the dots to do this best line, we would probably disagree when we look down in this corner and we're looking for those quote-unquote nice spots. So for myself, and yours might be a little bit different, but for myself, my best line crosses right over top of some grid lines right there. That's going to be a nice spot to go and make a slope triangle. I want to make this slope triangle huge, so I want to look like down in this left-hand corner. So that's a nice spot, and then I want to go up to the top right-hand corner and see if I have a nice spot. And I'd say, hey, that's a nice one right there. So I don't know if yours match that. If they do, fantastic. If they don't, you can go with your own. That's totally fine. And then what I'm going to do is I'm going to turn those into a triangle. So I'm going to grab myself my ruler and make a triangle out of that. And then we're going to use the triangle to find the rise and the run. There we go. There we go, got a nice slope triangle. Now, in order to find the rise and the run, we actually show some values on the slope triangle. So what we're going to show on the time axis is a little triangle, which means delta, or change in. And this says the change in time. It's a horizontal horizontal line that's matching up with my time axis, is equal to. Now, we find the run, the length of that line, by taking the biggest number that it touches. So you have to imagine taking this horizontal line and dropping it down onto the time axis. It would touch 3.6 at the far right side. And then we would subtract, where does it touch over on this end? We drop that point down, that's worth 0.2. We put our units, always put units on there, which are seconds. And then the weird part is we don't even put an answer. So we're actually just going to leave it like that. Now let's do the same thing with the vertical line, which is going to be the rise. So we're going to call this delta D, the change in distance. And this one might be a bit harder to see, but you have to imagine taking this vertical line and dragging it all the way over onto your distance axis. And we want to know what is the biggest number that it touches. So right there, if I trace that point over, I'm bang on 1.6 for mine. Yours could be a little bit different depending on if you had a nice spot there or not. And then my minimum, which is this corner here, I want to imagine dragging that all the way over onto my distance axis. That would be 0.08, two little boxes. So minus 0.08. I don't show my answer, but I do put units on there, meters. So there's one slope triangle. Now let's do another slope triangle for the maximum line. So I'll zoom in here. Let's look for those quote-unquote nice spots. Again, yours might not match with mine. That's totally fine. You can just fudge yours to match mine, or you can go with your own. It doesn't matter. We want to look for something down in this corner because we want that slope triangle to be huge. And I would say I've got a pretty nice one right there. Looks like that green line is crossing right over some grid lines. And then if I head up to the right-hand corner, oh yeah, right there. There it is. So now what we're going to want to do is draw another slope triangle. And you might want to go like up and over this time, just so that the two slope triangles don't overlap on each other. Zoom out even a bit more. So I would draw the other slope triangle, again, just so you don't have numbers on top of numbers. Let's go this way. Up and over. And then we're going to have to show the big and small numbers again. So we've got some nice big slope triangles. And on the time axis, maybe I'll just put it underneath so I can keep that time axis on the screen. The biggest number we touch, so I go to this corner and I imagine dragging it all the way down. That looks like 3.8. And the smallest time value we touch, if I go to this corner up here and drag all the way down, that's worth 0.5. I don't put my answer, but I do put the units of seconds. And then for distance, delta D equals the change in distance is take the top of that vertical line, it matches up with 1.8. And I'm going to subtract this corner, which matches up with two little boxes up, 0.08. Don't put an answer, but do put units. All right, so let's scroll down and just put a couple of notes here about the slope triangle. So here's what we did for the slope triangles. We want to make them big. They should take up like half of your page at least. So don't bail out and do tiny ones. Make them huge. You need to make sure that you draw your own. You and a partner will not end up drawing the same slope triangles, even if you and your lab partner have the same data. Because as soon as you draw a line, everybody's line is going to be slightly different, so it's unique. And that means you're going to have your own unique numbers on a slope triangle. So I should never see somebody with the same numbers on a slope triangle as somebody else, because that means one person copied the numbers off of the other. Very, very, very rare that you would have the same numbers on a slope triangle. And then we need to show something that looks just like this. Delta, whatever the axis is, and then big minus small. And then you want to put your units. That's a really common one to forget, is those units. And we would usually put them in brackets. So I'm going to stop this video just so that I don't make my computer light on fire. We are going to continue with a part B where we start actually doing a few calculations. So I'm going to pause. You need to go find the next video, which will be part B to this lesson.